Oh, okay, it's recording.
Amazing. Right. So again, we're talking about question top left corner, and it says choose the correct statement for the effect of dilution on buffer capacity. So we have the formula for buffer capacity is number of moles, difference in number of moles, divided by the difference in pH. Okay, so you have a solution, and then you dilute it. So when you dilute it, the number of moles stays the same, but the concentration decreases. Okay, and therefore when the concentration of the acid decreases, pH will increase because the concentration of H plus will also decrease. Okay, because you're having more volume. So if this expression decreases, that means that the whole of will decrease. Okay, so buffer capacity decreases with dilution. Again, we've got another question regarding buffer capacity. Buffer capacity increases with dilution. That's wrong. Is the lowest for pH equals pKa. That means that there's same concentration of acid and salt is not dependent on pH. That's wrong because you have difference in pH in the formula. Okay, and determines the ability to combine H plus and OH minus. That's exactly what it is, because it's basically it shows the ability of the buffer, okay, to take change. So to either accept H plus without changing pH or accept OH minus without changing pH. Okay, so it can combine H plus and OH to produce water. Okay, so therefore, if you produce water, then you're basically taking out the H plus or the OH minus out of the equation. And therefore, the ability of the buffer to stabilize the pH increases. Okay, so this is correct. Okay, so aqueous solution of sucrose is isotonic to the blood if its concentration is. I tried looking for this question everywhere. I did not find it. I did not find anything about sucrose concentration in blood. So if you do find it in the book, then that's great, because I couldn't find it anywhere else. Okay, so select two ions which concentration inside the cells are higher than those outside the cell. Okay. So I can start with calcium. I'm not sure about calcium because calcium participates in active transport. Okay, so therefore it has very high concentration inside the cell. So that's not true. Bicarbonate gets transported outside of the cell. So this might be correct because during the chloride shift phase of gas transport, hold on, where's chloride? Yeah, here. It gets transported outside the cell. Calcium, yes, calcium concentration is higher. However, phosphate, no. Sodium is higher inside the cell, and so is chloride, because sodium participates in the formation of action potentials, and it always has higher concentration inside the cell. Even if momentarily you'll have higher outside the cell, it still diffuses back in. And you have sodium-gated ions inside the cell, because sodium is used in a lot of metabolic processes. So the right answer for this one is the second option, HCO3 minus. Okay, so again, oxidation of glucose with enzymes. So we talked about weak oxidants, strong oxidants on galactose. During weak oxidation, you will have galacturonic acid. Okay, in strong oxidation, you will have galactaric acid. Okay, enzymes cannot produce the strong oxidation that you will get from strong oxidation oxidizing agents like nitric acid, but it can produce galactonic acid, okay, which is galacturonic meaning one carboxylic acid. So this is the intermediate. This is the weak one. Okay, so the enzymes do not produce strong oxidation, therefore they act as a weak oxidant and can produce galactonic acid, which is one carboxylic acid and one alcohol. Okay, okay, so hemoglobin buffer acts mainly okay, so first of all, extracellular, does it? No, it doesn't. It acts only inside the erythrocytes. It's not extracellular. That's correct. Urine? No. That's the bicarbonate and the phosphate. Skeletal muscle? No. We have another protein, which is myoglobin, and intracellular. That's correct, because it's inside the red blood cells, so it's intracellular. Okay, now onto the calculations, which is the easier part. These are the main formulas that you're gonna have to use. You might need more. You will find more in the book probably, but these are the ones that I found most useful in this book. The first question: a 60-year-old man with severe heart failure, pulmonary edema is okay. So you decide to give him 60 milligrams of furosemide, okay, and each ampule contains 50 milligrams, and each ampule is 5 milliliters. Okay, so if I can find the number of milligrams in 1 milliliter, and I multiply that by in 1 milliliter, multiply that by 6, before you will get the number of milliliters that you need for 60 milligrams, because each milligram has 10, each milliliter has 10 milligrams. Okay, so if you have 50 milligrams in 5 milliliters, then each milliliter you're gonna have 10 milligrams. Okay, so 10 times by 6, because you have 6 milliliters, because you have 60 milligrams, you'll get 6 milliliters. Okay, there's not much to that really. You just have to recognize what it is. This person has 8 milliliters, which I don't know why they did. If it's you, I'm sorry. If it's anyone, check out this. Okay, a stock solution of 200 milliliters and 12%. Again, percent. As soon as I see percent means grams in 100 milliliters. So there you have 12 grams. Then you have 200 milliliters. Okay, you have 200 milliliters of that. Is dissolved in 1,000 milliliter or 1 liter of water. Okay, determine the dilution factor. So first of all, I need to figure out the concentration for dilution. Sorry, the number of moles. Okay, because the number of moles doesn't change. If the concentration changes because you're adding more water, the number of moles doesn't change. It stays the same. But the volume, you have the moles are basically, or the volume dispersed in the solution. Okay, so you'll have 400. There are multiple questions that look like each other. Put it here. This is the answer to another question. Basically, it's not a big deal. What we can do is, so 12, you have 12 grams per 100 milliliters. You have 200 milliliters of that. So how many grams do you have? Okay, you have 200 milliliters and 12 grams in 100 milliliters. You're gonna have to times that by 2, which is 24. So you have 24 grams in a 200 milliliter. Okay, and the number of grams again doesn't change because all you're doing is just adding water. So the number of grams of sodium chloride is still going to stay the same. So you have 24 grams in 1,000 milliliter. Okay, so we need to determine the concentration in percentage. So concentration percentage is grams in 100 milliliter. Okay, so if we have 24 grams in 1,000 milliliter, now we're going to have 2.4 because you divide that by 10. Because the difference between 1,000 and 100 is 10. Okay, or a factor. So 2.4 grams in 2.4%. Going to be 2.4%, or 2.4 grams in 100 milliliter. And the dilution factor, well, it's gone from 12% to 2.4. So it's going to be 12 divided by 2.4, which is great, stop working. Yeah, it's 5. It's a dilution factor of 5. So you dilute it like it's now fifth of what it was, the concentration. Okay, so
also sorry to interrupt. So the dilution factor is old concentration divided by the new concentration, or
yes,
no? Yeah.
yes,
No, the
it's how
percentage.
no dilution is given as a number. So D equals 5. Okay, so 2.4%. is how much of 12? It's a fifth. So you're decreasing the concentration by a factor of 5. So D equals 5.
Oh, okay. All right, thank you.
Okay, so again, stock solution, this is the same question, but this time it has 400 milliliters in 1,200 milliliters. Okay? So again, same concept. 400 milliliters of 12 grams per 100 milliliters. Okay, so you have 400 divided by 100 is what? 4. Okay, so you need to multiply that 12 by 4. So how many? You have 48 grams in 400 milliliters. Okay, because essentially you have 12 grams per 100 milliliter, and you have 400 milliliters. So therefore, you multiply everything by 4. Okay, so 12 times by 4 is 48. So the value, that's the grams, the number of grams that you're going to have in the 400 milliliter, and it's also going to be the same in the 1,200 because you're only adding water. The mass of the sodium chloride doesn't change. So therefore, it's 48 grams in 1,200 milliliter. So that's going to be 0.04 grams in 1 milliliter, because 48 divided by 1,200 is 0.04 in 1 milliliter. And then again, percentage is grams per 100 milliliter. Okay, so we're gonna times that by 100, which gives us 4. So you're gonna have 4% or 4 grams per milliliter. And then again, same concept, 12%, and then you have 4%. What's that? What's the dilution factor? 12 divided by 4 is what? 3. Okay, so how many grams? Same question. Oh no, sorry. How many grams of sodium hydroxide need to prepare 40 grams? So 40 grams, in other words, is 40 milliliters. 40 grams of water is 40 milliliters of water. Okay, and so we assume it has the same density. 40 milliliters of 20%. Again, we said percent is grams per 100 milliliter. Okay, so you have 40 milliliters, okay, of 20 grams per 100 milliliters. Okay? So if you have 20 grams in 100 milliliters, how many grams are you going to have in 40 milliliters? Well, 40 is how many 40s in 100? Okay. And that comes out as, first of all, you can do that by finding the number of grams in 1 milliliter and then multiplying that by 40. Okay, so in 1 milliliter, how many grams? Well, 20 over 100 is 0.2. Okay, so you have 0.2 grams in 1 milliliter. You times that by 40, you'll get 8. Okay. 8 grams in order to prepare 40 grams of 20% sodium hydroxide. Next question: how many milliliters of medicament solution should be given to a patient weighing 20 kilograms? That is a child. The correct dose of medicament is 25 milligrams per kilogram. Okay, straight away, 20 kilograms and 25 per kilogram, 25 milligrams per kilogram. So I'm going to multiply 25 by 20 in order to find how many milligrams in total I need. 25 times by 2 is 50, so that's 500 milligrams. Okay. So, and then it says if 250 milligrams of medicament was dissolved in 20 centimeter solution. Okay, so straight away, I can see that 500 is double 250. So I'm going to need double the volume. So it's going to be 20 times by 40 milliliters. Okay, and then how many grams of sodium? Okay, so this is essentially the same as this question. This question is using different numbers. Okay, 60 grams of 20%. 20 again, percent straight away. I see percent. I'm thinking grams per 100 milliliters of sodium hydroxide. So first of all, I need to find the number of grams in 1 milliliter and then multiply that by 60. So again, 20 over 100 is what? 60 is 0. Yeah, 60 times 2 is 120, and then you have one decimal point, so it's 1.20. Yeah, that's right. Okay, so you're gonna have 1.20, no, 12 grams. Yeah, you're gonna need 12 grams. So there's an error here. There's this decimal point is supposed to be over there. So you're gonna need 12 grams for 60 grams of 20% hydroxide. Okay, next question. 23-year-old man was admitted to the hospital with diarrhea less than 4 days. So first of all, diarrhea, I'm thinking the symptoms of acidosis and alkalosis. So I can go up. I can think about, okay, alkalosis and acidosis. First of all, which one has diarrhea? There we go. One of the causes of metabolic acidosis is diarrhea. Okay. So I know straight away that's what I'm thinking about. This question has two parts, by the way, a calculation part and a theory part. Okay. He is weak and sleepy. Again, another symptom of respiratory acidosis, metabolic acidosis. Okay, he reports that several of his friends had similar symptoms before. Arterial blood analysis gave the following values. Given us the partial pressure of carbon dioxide and the concentration of carbonates, ions. Okay, so calculate the pH. So again, we've already seen this before, and it's calculating the pH of the buffer system using the concentration of the acid and the salt. Okay, so we're gonna use this equation, which is here. By the way, this is plus because I flipped the acid and the base. So if you look at the original formula here, you'll find that the acid here is base over acid. Okay, salt over acid. So therefore, this becomes a plus. It's the same. It's arithmetic. Yeah. So again, it's already given us the PAA, which is 6.1. Okay, and the dissolvability of carbon dioxide. Okay, so first of all, carbon dioxide is a gas, so therefore you don't have concentration of the gas because it's dissolved. Okay, so I need to figure it out, and the concentration of gas is basically the partial pressure, which is already given to us, 22, times by the dissolvability, which is 0.03 millimoles per liter per millimole. Yeah, it's the unit for partial pressure. So yeah, 22 times by 0.03 to find out the concentration of the acid. Okay, because carbon dioxide is what supplies, is what is the water is in excess, and you have carbon dioxide is what determines the concentration of hydrogen carbonate, which then dissociates to form the H plus. Okay, so carbon dioxide basically is acting as the acid here. Okay, so again, we have 0.01, which is the concentration of the carbonate ions because it's 10 millimoles. Again, this is something that we need to watch out for. Our concentration for using this formula is moles per liter, not millimoles per liter. So you need to divide that 10 by 1,000, which gives you 0.01. Okay, so we plug that into the equation, into the formula. So it's 6.1 plus log 0.01 divided by 0.66, which is 22 times by 0.02. Concentration of carbon dioxide. Okay, and that gives us a pH of 4.28. So this man is in very, very bad shape. Well, I don't think that's right, actually. I think there might have been a fault in, yeah, hold on the plus and minus. No, it should be okay. So yeah, this is very bad pH for blood. This man's in very severe metabolic acidosis. So that's the underlying condition, and that's the pH of the blood. This question, we've had another one that's very similar to it. 200 milliliters of 12% sodium chloride dissolved in 1,000 milliliter of water. Okay, so first of all, we need to find the mass of the sodium chloride that's been the original mass. Okay, so you have 12 grams in 100 milliliters, which is 12%. Okay, so in 200 milliliters, we're going to have 12 times 2, 24 grams in 200 milliliters. And then you dissolve that in 1,000 milliliters. Okay, so 24 grams in 1,000 milliliters. In other words, 2.4 grams in 100 milliliters, or 2.4%. Okay, so from 12% to 2.4%, dilution factor is 5. You had the same exact question before. Okay, so this is a new one. It says calculate the percentage, milligram percentage, and per milli concentration of the 0.4% millimole hydrochloric acid. Okay, so the way to doing this is, and then it gives us the molecular weight of hydrochloric acid. We need to use this equation. N equals M over MR. Okay. Yeah. So first of all, we have the number of moles, which is 0.4 moles in 1 liter. Okay, I'm going to assume the volume is 1 liter. So 0.4 moles in 1 liter. So we already have the number of moles, and we have the molecular weight. So we have 2 of these. What we are missing is the mass. That's what we need. Okay, so we need to rearrange this equation. So you have the number of moles times by the molecular weight, giving you the mass. So you have 0.4 times by 36.46. Okay, 34.46. And then you're going to multiply them together, which gives you 14.584. Okay, so that's going to be 14.584 grams in the volume, which was 1 liter. Okay, in other words, it's going to be 14.584 or 14.6 per milli. Okay, because per milli means grams in liters. Okay, grams in 1 liter. Okay, so you're going to have 14.6 grams in 1 liter, which then, well, 1 liter means 10 of 100 milliliters. Okay, so you divide that by 10 to get percentage, which is going to be 1.46. You just move the decimal point, and then for the milligram, you're going to multiply 1.46 times by 1,000. Okay, and that's going to give you milligram percentage. So that's how you do that. And then I think this is the last question. Is it? No, 2 more. Actually, this is the same concept, but it's only using 0.6 moles per liter this time. Okay, so you do the same, but you change, instead of 0.4 moles, 0.6 moles. So 0.6 times by 36.46. Okay, that would be the per milli, and then you can use that to find percentage by moving it 1 decimal point, and milligrams by timing it by 1,000, the percentage. Okay, so that's that. And then how many milliliters? Yeah, this is the same question. So this is the last question. How many milliliters of methamphetamine solution should be given to a patient weighing 30 kilograms? No, it's not clear because whoever was taking a picture had shaking hands. So yeah, 30 kilograms. We've essentially done the same question, but let's do it again. 25 milligrams in 1 kilogram. And the patient weighs 30 kilograms. Okay, so 25 times by 30, or to find the total number of milligrams I need. So 25 times by 3, that's 75. And then you have a 10 there, so 700. Okay, so 30 by 25 is 750. And then you have 250 milligrams in 10 milliliters. So you're going to times that by 3, because 700 divided by 250 is 3. Okay, and yeah, 3 times by 10 is 30 milliliters. That's what you're going to do. And that should be it for the questions that were tests. I hope I covered enough. If you do remember a question, oh yeah, there was another question. it said calculate the pH. I remember it, but I don't have it here. Calculate the pH of a solution which has concentration of OH minus or hydroxide ions, 3 times 10 to the minus 5 moles per liter. Okay, so this question is a bit of a trick one. pH equals 14 minus POH. POH is another value. Okay, and you can calculate POH the same way you calculate pH. First of all, we need to find POH, which is negative log 3 times 10 to the minus 5. And then you take 14, you take that away from 14, okay, which gives you the pH. And yeah, that I couldn't find it, but I do remember being sent that question. Do you guys have any other questions or anything that you struggle with, or is it clear enough?
No questions.
I have one question.
Yes, go ahead.
From one of the calculation questions, the ones that were like where you got a percentage of something and then 200 milliliters. And then you always said you have to multiply it. So then you have like 24 grams in 200 milliliters. I'm not sure which question that was. It's like 200 milliliters and 12%. Yeah, exactly.
Oh,
that one.
No, that's 400.
Yeah, basically the same thing though.
It is,
and
yeah.
I was just wondering how like the connection between going from 24 grams and 200 milliliters to the 24 grams in 100 or 1000 milliliters, because like I would have thought that you would have to multiply 200 milliliters to get to 1000 rather than just making the 24 grams in 1000 milliliters.
That would be correct if the concentration stays the same. However, we're diluting here. So what it means is that let's see. Okay, it's like having
Sorry, I can't hear anything.
we have, can you hear it better now?
Yes.
Okay, so essentially what this question is saying, it says that you have 200 milliliters of 12 grams per 100 milliliter, okay? So now I need to multiply by 2 because the concentration is 12 grams per 100 milliliter. That's the concentration. It tells me there is 12 grams in each 100 milliliter. And I have 200 milliliters. So therefore, I'm going to have 24 grams in the 200 milliliter, okay? Which is these two, for example, okay? So the concentration now is 2 pennies or 20 pence per hand, okay? However, I'm going to add 1000 milliliter. I'm going to dissolve that in 1000 milliliter, okay? So I'm going to make the whole solution have volume of 1000 milliliter. Okay, so I'm not adding any more pennies. Concentration is the same. The concentration is not the same as before, but I still have the same number of pennies. I'm just putting it in a larger space. So the concentration is penny per 100 milliliter. Does that make sense?
Yes, thank you. And
yeah.
I think just lastly, this was already brought up, but like I think I got confused again. So for the oxidation of galactose with a weak oxidant, we get galactaric or galacturonic acid. I forgot which one was which.
Galactonic is when you have.
Galactaric is the one for the weak oxidant.
Yes, galactonic is one. And galacturonic is one. So also moderately.
I just got those messed up.
Yeah, that's okay. Galactaric is carboxylic acid on both. Is that it then?
Thank you.
No problem. Okay.
Just one more thing.
Guys. Yes.
So the enzyme is a weak oxidant, right? Enzyme?
Yes, yes. Because in the body, you cannot get something like, you cannot get high concentration of nitric acid because it's very corrosive. It will be very harmful. So yeah, and enzymes it can all what's it called? The activation energy by so much. They cannot lower it so much that you can get strong oxidation. So yeah. Is that everything then?
Oh yeah.
Thanks for attending.
So.
Thank you so
Thanks
much.
for-
you.
This is honestly
I
really
know it's.
helpful.
I'm glad it was. There's not a lot of people today, but hopefully because everyone's going on holiday for it. So, anyways, thank you, and hopefully I'll make another one for the next chemistry lecture if I'm back in Poland. So
Oh yeah,
Yeah.
and the presentations that you amazingly created for us, where do we get those? I don't remember.
yeah, so you have the UMed Survival Guide group. We usually, me and Haitham, we post everything we have on
I
there.
think I only saw like anatomy things. I couldn't find the.
Yeah,
I'm
that's
not
probably
sure.
because you joined late. You know what?
Oh,
Leave
sorry.
it to- I'll ask. No, it's because like we started the group a while ago, and then we sent everything on there. So we'll send everything again, make sure that everyone has it now. So yeah, I'll say tomorrow it should be up. Everything should be up.
Okay, thank you.
Yeah, thank you so
Right,
much.
and thank you so much, and please send me the video.
Oh yeah, for sure. Right now.
Yeah, I really appreciate it because I tried converting 2 last time and it only gave me 1, so I was like, oh, okay.
So
yeah.
do I click pause recording now or what? Like, or stop recording and then it'll
Yeah,
save?
yeah. Stop recording and then it will convert. It usually takes like 10 minutes, and then yeah, you can send it with it wherever you.
Okay,
You can,
because
you can keep it as well.
this dorm Wi-Fi, man, it's gonna take a while, I think.
Yeah. Oh, you're living in the dorms.